Hello, my name is Garrett Summers. I am a graduate student in the Ohio State University Astronomy Department, and today I will be discussing my recent paper written in collaboration with Dr. Mark Pinsonneault entitled Rotation, Inflation, and Lithium in the Pleiades. Our paper is concerned with understanding the origin of lithium abundance patterns in young clusters. Lithium is a fragile element and is readily destroyed in stellar interiors during the pre-main sequence. The exact amount destroyed depends strongly on the mass and composition of individual stars, so theory predicts a characteristic abundance pattern as a function of temperature on the main sequence, with very little dispersion. However, lithium abundance measurements of the Pleiades, a young nearby open cluster, have cast doubt on this simplistic picture. For over 2 decades, it has been known that the Pleiades shows a nearly order of magnitude spread in inferred lithium abundance at temperatures around 5,000 Kelvin. The cause of this dispersion is still debated, but a crucial clue has motivated several attempts at resolution. That is, the most lithium-rich stars tend to be the most rapidly rotating. Previous theoretical studies of the influence of rotation on lithium abundance suggest that rotation should increase the rate of destruction and therefore lead to a lower abundance. But this would produce an effect opposite the sense of this correlation seen in the Pleiades. How then might rotation induce this dispersion? In our paper, we suggest that this spread is created by variations in the radii of pre-main sequence stars correlated with rotation. That is, at fixed mass, faster spinning stars are physically larger than slowly rotating stars. In stellar models, radius inflation leads to a reduction in the temperature of the interior of the star. Since lithium burning is extremely temperature sensitive, a radius inflation of about 10% can suppress the destruction of lithium by more than a factor of 10 at some masses. This idea was motivated by the growing literature of precisely measured radii of rapidly rotating active stars, which are sometimes found to be larger by 10 to 20% compared to slowly rotating inactive stars, both on the pre-main sequence and on the main sequence. The goal of our paper is to use a stellar evolution code to calculate the lithium pattern expected from a correlation between rotation and radius inflation on the pre-main sequence. To this end, we first reviewed the individual impact on lithium of rotation and radius inflation during the pre-main sequence. We find that rapid rotation tends to accelerate the destruction of lithium since rotational mixing efficiently transports heavily depleted material from the stellar interior into the convection zone during this epoch. On the other hand, we find that an inflated radius tends to strongly inhibit the destruction of lithium during the pre-main sequence, since a puffed-up star has a cooler convection zone base, and lithium proton capture reactions therefore occur much less frequently. These conclusions are broadly consistent with the findings of previous studies. Next, we calculated the first stellar models, which include both the effects of rotational mixing and radius inflation. We find that the inflationary inhibition of lithium destruction and the rotational acceleration of lithium destruction cancel out to a great degree in our models. An interesting result comes out of these models when comparing a rapidly rotating inflated isochrone to a slowly rotating non-inflated isochrone. When this is done, we find that the most rapidly rotating stars are the most depleted in lithium above the solar temperature, whereas the most rapidly rotating stars are the most abundant in lithium below the solar temperature. This is an intriguing result, as the correlation for lower mass stars is exactly the kind found in the Pleiades. Thus, our models tentatively suggest that a rotation-inflation connection during the pre-main sequence could produce the observed lithium rotation correlation. Next, we tested whether this qualitative notion could realistically explain the observed lithium pattern in the Pleiades. To do this, we generated a number of synthetic cluster distributions which follow various prescriptions for the dependence of inflation on rotation. First, we tested 3 limiting cases which represent distinct classes of physical models: no radius inflation regardless of rotation, uniform 10% radius inflation regardless of rotation, and inflation uncorrelated with rotation. In each case, we find that the resulting distribution is strongly at odds with the empirical Pleiades pattern. The first 2 cases cannot reproduce the dispersion seen in the empirical pattern, and also cannot produce the required correlation between lithium abundance and rotation rate. The uncorrelated case produces a qualitatively accurate dispersion and median as a function of temperature, but no lithium rotation correlation. We conclude that no inflation on the pre-main sequence, uniform inflation on the pre-main sequence, and uncorrelated inflation on the pre-main sequence are all ruled out. Finally, we tested a case where radius inflation correlates with rotation, such that the slowest rotating models are not inflated and the fastest rotating models are inflated. Both the width and distribution of the empirical pattern are naturally predicted as a function of surface temperature, and we see a stark correlation between rapid rotation, denoted by larger circles, and high lithium abundance. This is the first physically consistent model which reproduces the observed Pleiades pattern, so we conclude that a correlation between radius inflation and rotation is a strong candidate for solving this long-standing mystery. Thank you for watching, and please remember to check out our paper appearing on AstroPH.